this is expectation maximization. So it is a way to do maximum likelihood estimation. Initially it was proposed as a way to do maximum likelihood estimation when you have missing data. Okay. So suppose you are given data x, which is what you observe and is incomplete, it's known to be incomplete, but there are some values that are missing, and you want to estimate the maximum likelihood, you want to get the maximum likelihood estimates of the parameters which are unknown. But here you are assuming two things. You are assuming that there is some parameterized family, you are doing some parameterized fitting, which is for which the joint likelihood is easy to compute. Okay. So we denote by x and z the complete data, the observed data plus the hidden data, and we assume some parameterized family from which this data is generated, like a Gaussian or exponential or something like that, and we do not know the unknown parameters which we want to estimate. So we start seeing connections with what we have seen in the case of Gaussian mixture, because if you take the marginal probability here, you again see a summation coming inside the log, right, and this again poses problems, right, and they need not be of the same family. So if they have a joint exponential, it does not mean that you will have the marginals coming from the same family. Okay. So EM as it is most commonly used now was proposed by Dempster, Lade and Rubin in their seminal paper, Maximum Likelihood from Incomplete Data via the EM algorithm. This was in 1977, and even before that a lot of statisticians mostly, they have developed EM like algorithms, but usually when we cite EM we usually cite the 1977 paper. So
could you explain the slide 17 again?
Slide 17. So this is the problem. Okay. You have incomplete data, you have hidden data. Yeah, I forgot to mention something. For the rest of the discussion, we will assume that this hidden data is discrete, but all the derivations will work if you assume this to be continuous as well. You just have to replace the summations with the integrals. So you have observed or incomplete data and hidden data. The complete data is the combination of these two. You are assuming some parameterized family for the complete data, and you want to estimate the parameters. This is the problem that EM solves. Okay, and now we will see what EM is. So EM is an iterative algorithm, just like what we designed for Gaussian mixture. You again start with a guess of the parameters that you have. You evaluate your first guessed likelihood, and then you iteratively do two steps. First, compute the posterior distribution of z given the current estimate of the parameters. Okay. After that, you compute the expected complete log likelihood under this distribution. Right. So we will call this a Q function. Okay. Now notice that this expectation takes the complete data likelihood. Here the parameters are unknown, right, and this expectation assumes the distribution of z given the parameters that you have guessed in the previous round. Okay. And then you again get a new guess, and that new guess is got by maximizing this Q function and taking that argument theta, curly theta, which maximizes this Q function, right. So I think I have it there. What we wanted was to get the maximum likelihood estimate of theta, right, and we see x, but x is not complete, x has some missing data z. So and so we express this as a marginal distribution of the complete data, right, and we get into the same problem of the summation being inside the logarithm, right. So we decide to not compute the maximum likelihood in this way, but instead compute the maximum taking the expectation of the log likelihood of the complete data, but again we under the distribution of z, but we do not know the real distribution of z because we do not know the parameters. So we take the guess that we had in the previous round, right. So we compute the expectation of the complete data likelihood under the distribution of z given the current guess of the parameters, and this works. We will see why it works, but this works. So the entire EM algorithm can actually be represented by just this one line. You start with some guess, and then for the next guess you calculate the expectation of the complete data log likelihood under the distribution of the missing data using the previous guess. And this can actually be this is broken down into two steps, where in the E step you compute this expectation, and in the M step you maximize and get the parameters, maximize this Q and get the next set of parameters. Okay. So let us see how we can get the EM algorithm for Gaussian mixtures. The key thing here is we did not assume anything, we did not say anything about hidden variables, but the trick here is to use these latent variables as hidden variables, and this is how EM is used in a lot of different models, not just Gaussian mixture, lot of latent variable models. You assume that the latent variables are hidden, you do not know them, and run the whole EM machinery. Okay. So this is just a reminder. We have the Gaussian mixture model where we want to estimate all the parameters represented by curly theta. You have k components, pi k, mu k, sigma k for each component, right, and what we want to find out is the maximum likelihood estimate. All right. Do we have time for this? Yeah. So let's write this down here. Yeah, the most important thing to remember is that this distribution is taken over the previous guess, whereas the expectation is for the complete log likelihood over the unknown parameters, right. And the M step just gets the next guess Alright. So, if we want to get the maximum likelihood parameters, we first need to compute this Q function, and then usually this step is easier. It is just the expectation that requires some work. Once you get Q, then the maximization step is just computing the derivatives. And as you can see, this works only if the E step gives you something which you can easily maximize, right. And in the case of Gaussian mixture, we will see that by using the complete data likelihood, we will be able to get something that we can easily maximize. So, let us see this one by one. The Q function is, this is just by definition, it is the expectation of the complete data likelihood using under the distribution of Z given the previous the guessed parameters, right. So, this log likelihood is just the log, this is the likelihood of xn zn given the unknown parameters over all the data points. Now, I can take this summation outside by linearity of expectations. So, the summation goes in, the expectation is here, and now this complete log likelihood can be written in this form, right. So, we can derive this formally, but intuitively it is very clear. You see, this is just an indicator function which gets a value of 1 when Zn is equal to k, gets a value of 0 when Zn is not equal to k. So, this product, in this product there will be only one term which will have all the terms except one will get an exponent of 0, and so you will have 1, and only one term out of the k will remain for this, right. And so, the log likelihood is just it comes straight away from this formula after using the indicator function here, and this gives us the complete data likelihood. Alright, so then after that the product becomes a sum when you take it outside the log, and the exponent comes down, and again the expectation can be brought inside by linearity. So, you get both the summations out, and with respect to the distribution of Z using the previously guessed parameters, this is just a constant. So, the expectation is only over this indicator function, right, and this indicator function, expectation of an indicator function just gives us the probability, and you have the probability of Zn equal to k, again given x and the previously guessed parameter values, log just remains. So, this is again the responsibility, is the posterior probability of Zn equal to k, but in this case this responsibility is not with respect to the original parameters. This posterior probability is with respect to the guessed parameters, right. So, I am indicating that by this subscript here. So, it is the responsibility times the log that remains. So, what have we achieved? The reason, so we have got an expression for Q in terms of again the responsibility, but this time the responsibility is with respect to the guessed parameter, and if you just look at this function, you can see that this is easier to differentiate because the summations are all outside and the normal distribution will come here, and the differentiation will be just like what you do for in the case of fitting a single Gaussian. Okay. And how did that happen? It happened mainly because we were taking the complete data likelihood. The complete data likelihood gave us a nice mathematical form here, which due to the expectation all the summations got pushed out, and we got this nice form for Q. Any questions here? No?
So, only because because the summation is inside the algorithm, we need to do all this. Otherwise, we can skip the whole thing.
Yeah, but EM is so that comes in many contexts, not just in the case of Gaussian mixture. In a lot of those cases, EM is useful. Yeah, but it's if you could get the maximum likelihood easily, you wouldn't need to use EM for Gaussian mixture, of course. Yeah. Now the M step is just this, which is we differentiate with respect to each of the parameters. So you have the Q function, right, and this is the same Q function here. Now one thing to remember here is that this parameter, the guessed parameter at the previous iteration, we know these parameters, so we know the responsibilities. So the responsibilities are just constants in this case, right, and so differentiating this becomes very easy. So this is with respect to mu k, this whole term is not necessary, we focus only on this term, and we again get, so this is for each of the different components, you get the entire normal distribution here, and no summations, log of this is exactly the same derivation as for a single Gaussian, right, and you use the same, you use matrix derivatives to get very simple forms here, and you can get, you will see that you again get back mu k, the same form that you get, the same form that we saw earlier for our guess, for our ad hoc iterative algorithm, except that these responsibilities are with respect to the previously guessed parameters. Okay. Right. So when we do this for sigma k, again we don't need to worry about this part, we only differentiate for this part. This is also very simple. You can simplify this further by first applying the logarithm here for each of these parts, and then the logarithm for the determinant is given by a simple formula. You can apply the logarithm here, I mean derivative here, and again you get back the same form for sigma k which you found earlier. So what and similarly for the m step for pi k, right, this time this term is not, this term goes away, you use Lagrange multipliers to get to add this term and differentiate this function to again get, so this is quite straightforward, you can check it yourself, right. So what have we done? We first found these same formulas by assuming that we know the responsibility, and then we used the EM steps to find that these values are exactly the same as what we found earlier, right. And if we plug this into the EM framework, so this is the EM framework, you start with a guess, you iterate by first finding the posterior distribution of z, and then you find the expected complete likelihood under this distribution of z, and finally maximize to get the new guesses, right. So the posterior distribution of z just gives us the responsibilities, and then this derivation we have seen, this gives us the next set of guesses, right, and this iteratively we can check for convergence. When the likelihood does not change much, we stop, and that is the EM algorithm for GMM. I have still not told you why this works, but we will see that, we will see the theoretical properties of why this is why this works well. Okay. Yeah. yeah, I just wanted to show you that what we have got through by doing all the math for EM is exactly the same as what we found during the iterative algorithm that we guessed. Okay, so let's do one more thing for today. Let's look at a special case. Let's assume a Gaussian mixture model where the covariance of each component is fixed to be epsilon times the identity matrix. So, epsilon is a fixed constant. You have epsilon times identity will give you a spherical Gaussian. We also fix pi k. Pi k is, so each component gives exactly the same contribution towards the Gaussian mixture. Now, the only parameter to estimate is mu k, right. So, when you since pi k is known, since sigma k is just epsilon times identity, the formula for the normal distribution simplifies to just this. Okay. So, this is identity, this goes away inside, you just have epsilon from here. The formula for the responsibility also simplifies, you just plug this probability of xn given theta k here and you get ratio over the, so you get just the exponential here and the sum over the different exponentials here. Now, if you look at this expression and see what happens to the denominator as epsilon tends to 0. Okay. As epsilon tends to 0, the term for which this difference is smallest will go to 0 most slowly. Right. And so, the responsibility will tend to 1 for that particular, that jth component here, because the numerator will be equal to the denominator in the limits, and for all others the responsibility will go to 0, right. So, this is the special case of hard clustering that I was mentioning earlier, right. And what it turns out to be is just setting the responsibility to 1 for that component where the for that component where the data point is closest to the mean, right. Otherwise the responsibility is 0, right. So, what are we trying to say? The responsibility is just the posterior probability of Zn being equal to k. For the nth data point we want to know which component it has come from, right. And you are saying the responsibility is set to 1 for that component where this is with respect to a particular data point, the nth data point. For the nth data point the responsibility is 1 for that component whose mean the data point is closest to, and it is 0 for all others, which means if you look at the data and look at xn and want to know the posterior probability of which component it came from, it is that component whose mean that data point is closest to. And let us do the EM for this. So, EM, the first step is to calculate Q. So, you plug in this formula, this formula it is the same as before because we are doing Gaussian mixture, it is just a special Gaussian mixture. And when you do the differentiation here with this simplified normal distribution, you again get the same formula, but the only difference is that this responsibility is defined in the way it was earlier, right. But what is it basically saying? It is saying the same thing, that you set the mean as, so for the kth component you take all the, so all the other responsibilities will be 0. So, you take only the kth component, for whatever is assigned to the kth component take all those data points and take the mean of those data points. So, this is the general EM. We first calculate the posterior distribution of Z, which we saw is exactly this. You assign the latent variable of xn to the closest mean, right, and then set the new mean as the mean of all data points with the same latent variable, right, which is just the k-means algorithm, right. So, you are assigning xn to the closest cluster with the cluster center mu k, and then re-estimating the cluster centers as the mean of all data points that is assigned to that cluster. So, k-means is just a special case of Gaussian mixture where the covariance matrix is is epsilon times the identity matrix. That is why you just have to compute the means, you do not worry about the covariance, right, and it follows the same framework of EM that we saw. Okay. So, I think we will stop here, because after this we will talk about all the theoretical properties of EM and why. Oh, I wanted to show you one more thing. Yeah. So let's take this this data. It's generated from 3 Gaussians. These are the 3 Gaussians and their cluster centers. This is what the data looks like. This is the density, and if we run EM once on it and plot it, you see it recovers, well, you have to believe me in this case, but it actually recovers exactly the means and covariances exactly how the way it was generated. Okay. And now let's run it 10 times. And plot it. So, I ran EM 10 times, and what I am plotting here is on the x axis we have iterations, and on the y axis we have the likelihood. In each iteration the likelihood keeps increasing until it reaches a point and remains steady there. So, this is a property of the EM algorithm which we will prove on Friday, that the likelihood always increases during the iterations. Okay. And now let's look at these 10 likelihoods. So, these are the 10 values of the when we stopped the iteration. So, usually if you see the slides, you will see that I have always put t here, which is like a hard bound on the number of iterations, because sometimes the likelihood may not converge, right. And so, we usually give a hard we give an upper bound on the number of iterations as well and stop it there. So, these are, when I ran EM 10 times, those are the 10 final likelihood values that I got, and the minimum is 4. So, in this case the likelihood values, this is a very easy case. So, yeah, this demo is not going to work now. Okay. So, I made a mistake. The reason is I gave k equal to 3 here. So, it is okay. So, you see what it has done. I gave k equal to 5. So, it has estimated 5 different components. You see, these are the means of the components. Right. So, it has tried to fit 5 Gaussians instead of 3. So, this is a more difficult case because the 3 components are not very well separated, and now if we run the EM algorithm 10 times here, so you see in this case this was the data, EM ran, the likelihood always increased, but what it estimated was this, right. So, when the data is very well separated, like we saw earlier, EM will usually give very good results, but when the data is not very well separated like this, it starts giving very weird results. Yeah. But no matter what it does, the likelihoods will always increase. Thank you.